So, this is a continuation in our series of videos in which we're looking at solutions to CSEC Physics 2024. And we're looking at question 4 in this video. Now, question 4 deals with electrical circuits. And so we'll be looking at question 4. So, part A of question 4 says, Figure 8 shows a circuit diagram with a low voltage power supply circuit which can be used to test whether a given material is a conductor or insulator. Um, Describe the procedure. So we're told to describe the procedure which would be used to test whether describe the procedure which would be used to test whether the material is a conductor. All right. So as we're told in the circuit, or we're told in information, um, this circuit can be used to test whether a given material is a conductor or an insulator. Now, what are the components in the circuit? So in the circuit we're told it's a low voltage power supply or a cell, and of course we have a lamp, which of course is to be used as an indicator of whether a current is actually flowing in the circuit. We of course have a switch, and of course we have two terminals, between which we typically place our component. Let's call those terminals X and Y. So we would basically place our component between the terminals X and Y, and then of course we would close our switch and then see what happens. So these are the steps that we could actually follow. So we could say that place a component or connect the components. Let me put it that way instead of saying place. So we're going to say connect the component between terminals X and Y. And then two, after we do that, we then close our switch. Close the switch. And after our switch is closed, we then basically observe the lamp. Right? We observe the lamp. And those are three simple steps that we could actually use to check whether a component is a conductor or an insulator, right? So we connect the component that we want to test between the terminals X and Y. We close our switch, and then of course we observe the lamp. Now, what should we expect if, for instance, this material is a conductor? If the material is a conductor, then of course we now have a closed circuit, and that means that electrons and electric current are able to actually flow around the circuit and the lamp may light, right? We would assume that the power supply is strong enough to actually turn on the lamp, and therefore if we connect a conductor between X and Y, you would expect that the lamp will be turned on, and that in itself would be an indicator that the material is a conductor, right? However, if it's an insulator that we place between X and Y, we know that insulators do not readily allow the passage of an electric current, and as such, no current would pass through X and Y, and it therefore means that the lamp would not light, and that would be enough evidence that the material is not a conductor, but an insulator, right? So that was part I of that part of the question, right? Where's my cursor? Where's my cursor? Oh, what's happening there? All right, so where is my cursor? My cursor is here. All right, so let's proceed to part 2 of the question. So since we're talking about conductors and insulators, the next part of the question says, name one material which is an electrical conductor and one which is an insulator. So in terms of the conductor, a common material is of course copper. We know that metals generally are very good conductors of not only heat but electricity as well. So a lot of metals are used in electrical circuits. But for the most, probably the most commonly used metal is of course copper. A lot of the wires in our electrical circuits are made of copper because of course copper is a very good conductor. And so this conducting material that we want to make mention of is of course copper. So for the conductor, you would say copper, and of course for the insulator, right? If you think about your connecting wires or cables, obviously most of them are usually encased or in an insulating material, which is of course rubber or plastic. Well, we could say rubber. right? So an insulating material could of course be rubber, right? Good, 2 marks there. Now, part 3 says, on the diagram in figure 8, mark the direction of electron flow. So let's look back at this diagram right here. So let's imagine that we place a component, a conductor between X and Y. So we now have a closed circuit, right? We now have a closed circuit. Now the power supply is going to drive a current, and it's going to drive a current I. Now, when we draw electric circuits, we usually show the direction of conventional current flow. Now, conventional current would basically flow in the direction that positive charge would move, and it therefore means that electrons which are negatively charged would flow in the opposite direction. So in this particular circuit, the conventional current I would flow from this end, the positive terminal of the battery, around the circuit in what that direction is that now? In an what's that? Anti-clockwise direction. And however, if we're talking about electrons, the electrons would flow in the opposite direction in a clockwise direction about around the circuit. Because electrons, of course, would flow from the negative terminal of the battery, where there are surplus of electrons around the circuit, and they would then be deposited onto the positive terminal of the battery. All right. So that would be the direction of electron flow from the negative terminal around the circuit in a clockwise direction. All right. So 1 mark for that. Now let's move on to part B of the question. Now, part B shows a circuit. Says figure 9 shows a circuit diagram which has a combination of 4 resistors and an ammeter A, right? Says calculate the reading of the ammeter when the switch is open, right? So let's check what is happening here. Now, we have a battery. It's a 12-volt battery. This 12-volt battery, imagine, is going to be driving a current I, which of course would be measured by the ammeter. The total current I will flow through this 3 ohm resistor, and then of course the current comes to this point here, right? It comes to that, well, you could say that junction, right? Let's call it junction A, and let's call this junction B. Now, because this switch is open, it means that no current will actually flow through that branch of the circuit. And essentially, with the switch open, the 3 ohm resistor is not a part of the circuit. So with the switch open, the entire current I would flow through this 6 ohm resistor, continue here, and then flow through the 1 ohm resistor. So with the switch open, essentially, the circuit looks like this. We have our battery, right? We have our ammeter, A. We have the 3 ohm resistor. We have our 6 ohm resistor. And now essentially we have our we have our 1 ohm resistor, right? So as I said before, with the switch open, this 3 ohm resistor is essentially not part of the circuit. And so is the effective circuit basically looks like this when the switch is open, right? And so basically we have our 3 ohm resistor, we have our 6 ohm resistor, and our 1 ohm resistor. This is positive, negative, this is 12 volts, and the total current being driven is I. So with the switch open, essentially these 3 resistors are connected in series, and we can therefore say their total circuit resistance RT is equal to 3 ohms plus 6 ohms plus 1 ohm, which gives us 10 ohms. So once again, when the switch is open, the 3 ohm resistor connected directly to it is essentially not part of the circuit, and the remaining 3 resistors, the 3 ohm resistor, the 6 ohm resistor, and the 1 ohm resistor are connected in series. And so their total circuit resistance is 10 ohms. Now, since you want to find the reading of the ammeter, of course, the ammeter reads current, and so what we want to find is the total current I that is flowing in the circuit. And of course, according to Ohm's law, in the form of the equation, we have V is equal to IRT, which therefore means that the current I is equal to V over RT. And so the current I would be equal to 12 volts divided by 10 ohms, which gives us 1.2 amperes. And therefore, this means that the ammeter reading with the switch open is 1.2 amperes. All right? So that's the first part of part B. Now, part 2 says, now, we want to find the ammeter reading when the switch is closed. Now let's go back to the original diagram and now analyze what happens to the circuit when the switch is closed. So going back to the diagram, see what is happening now. So when the switch is closed, so let me draw the switch here closed, right? So we have the switch closed here. Good. Now when the switch is closed, the battery, of course, will drive a current I. This entire current will pass through this 3 ohm resistor and it enters this junction. Let's call this junction A. So this is junction A, and let's call this junction B. Now at this junction, the current sees two paths in which it can flow. So what does the current do? It splits. The current splits, and the portion of the current, let's call that I1, flows there, and another portion, I2, flows through this 3 ohm, 6 ohm resistor, right? So at junction A, the total current I splits, and the portion I1 flows through the 3 ohm resistor, and the second portion flows through the 6, sorry, um, portion flows to the 3 ohm resistor I1, and the second portion I2 flows to the 6 ohm resistor. Now, what does this mean about how these two resistors are connected in parallel? Now, because the current splits at junction A, then any resistor through which the branch currents I1 and I2 flow would of course be in parallel, right? So because I1 flows to the 3 ohm resistor, I2 flows to the 6 ohm resistor, and they're in the different branches, it means that these two are parallel. So the 3 ohm and the 6 ohm resistor are connected in parallel. But of course, that combination is in series with the 3 ohm resistor, which is also in series with the 1 ohm resistor. So basically, let's work out the effective resistance of the parallel combination. We know that if we have two resistors in parallel, we can use the formula 1 over RT is equal to 1 over R1 plus 1 over R2. The common denominator, of course, is R1, R2. That into that leaves R2. R2 times 1 is R2 plus R2 into that leaves R1. R1 times 1 is that. And so we can say that. And if we reciprocate both, then 1 over RT, well, 1 over RT is equal to R1 plus R2 over R1, R2, which therefore means that RT, not R2. So RT, the total effective resistance, is equal to R1, R2 divided by R1 plus R2. So what this basically shows is that if two resistors are connected in parallel, their total effective resistance is simply the product of their resistances divided by their sum. And so for the parallel branch, we can say the effective resistance, let's call it Rp, would be equal to 3 times 6 divided by 3 plus 6, which gives us 18 divided by 9, which gives us 2 ohms. So essentially, this parallel combination of 3 ohm and 6 ohm resistor are essentially equivalent to a single 2 ohm resistor. All right. Now, with that done, we can actually redraw the circuit. So simplify it a little bit. And this is now what the circuit essentially looks like. All right. Let me draw it. So we still have our 12-volt battery, right? So 12-volt battery. We still have our ammeter A, right? We have our 3 ohm resistor, but this 3 ohm resistor is now essentially in series with a single 2 ohm resistor, and then that combination, of course, is still in series with the 1 ohm resistor from before. So we can put it there, but essentially, yeah, it's still in series, right? So this is the 1 ohm resistor here, right? So basically, that's our circuit, right? So we have the 3 ohm resistor, the 2 ohm resistor, and of course, our 1 ohm resistor, plus minus total current I flowing. And this, of course, is our 12-volt battery. All right, so we're not finished with that part. So now we need to find now the total circuit resistance and then find the total current flowing. So for this piece now, we can say that the total circuit resistance RT, we're just going to add them up now because they're in series. So this is basically 1 plus 2 plus 3, which gives us 6 ohms. And then, of course, we know that I is equal to V over RT, which gives us 12 volts divided by 6 ohms, which gives us 2 amperes, right? So we notice that when the switch is closed, we actually have a larger current flowing, and that is due to the fact that once you connect resistors in parallel, their effective resistance is going to be less than even the smallest resistor in the parallel combination, right? So in this particular case, because we had a 3 ohm and a 6 ohm in parallel, it meant that the overall resistance of those three in parallel would be less than 3 ohms. And of course, we saw that when they're connected in parallel, this contributes to a slight reduction in the total circuit resistance, which results in a larger current flowing, right? So indeed, as we saw from the previous part, when the circuit was open, current of 1.2 ampere flowed, but with the switch rather, when the switch now closed, a current of 2 ampere flows. All right. Mm-hmm. Now, the last part of the question says, calculate the power dissipated in the 1 ohm resistor when the switch is closed. So if we go back and look at the 1 ohm resistor to analyze the circuit here, we see that the total current I would flow through the 1 ohm resistor. And this total current flowing I that we just found is of course 2 amperes when the switch is closed. So we can basically say that the power dissipated P is equal to I squared R. And so P is equal to 2 squared times 1. And therefore P is equal to 4 watts. Right? So that means that this 1 ohm resistor will have a power dissipation or of 4 watts. So 4 watts of power will be dissipated in that resistor when the total current flowing of 2 amperes flows through it. Right? So this was the end of question 4 from CSEC Physics 2024. It wasn't the most wasn't exactly an easy question, but with the proper preparation, students should have been able to manage this question. And I imagine that some students would have some difficulty in analyzing this circuit, but it seemed to be quite manageable. Seemed to be quite manageable.